Good morning. This is Tim Stewart. I am president at Visual Decisions, and we're here today to talk about how to improve OEE using I-IoT, or the Industrial Internet of Things. At Visual Decisions, we've been in the business of improving business utilizing information from the shop floor since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements, such as a 30% increase in OEE, 50% scrap reduction, and much more. We have a unique approach to work with our customers to adapt processes to take advantage of the new capabilities and help establish a true data-driven manufacturing culture. Just as a quick note, if you have questions, please put them into the Q&A, and I will answer those at the end of the presentation. All right, so why OEE and why I-IoT? First of all, for those of you on the call that don't know, OEE is a composite manufacturing performance metric. It's a single metric that represents the health of the manufacturing process. It looks at availability, which is whether the equipment is running or not running, the performance, whether it's running at the speed it's supposed to run, and also quality as to whether or not the product being produced is being produced correctly on the first try. And so a machine or a line with a OEE of 100% runs 100% of the time that it's scheduled. It has zero loss for changeovers, cleaning, breakdowns, or any short stop failures. It always runs at 100% of its full rated speed, and it has zero defects. So if you can get a line that produces, or a machine that produces at that quality, then you certainly have something that's worth shooting for there. From links to financial performance, if you have better OEE, you can get increased revenue because if you can make more, perhaps you can sell more. It can reduce your cost of goods sold, certainly from a material cost. If you're scrapping less, you'll have reduced labor or reduced material cost. You can reduce your direct labor that's required. Outsourcing, if you're outsourcing due to capacity issues, indirect labor, indirect materials, logistics, maintenance, all of these things are impacted directly or indirectly through OEE. There are a lot of different improvement platform alternatives for improving OEE. MES or MOM systems are very much very prevalent in the improvement of OEE, and gather a tremendous amount of information from the shop floor to make that possible. Dedicated OEE solutions are available that allow you to connect to the machines, pull information from them, and utilize that for continuous improvement. There are systems out there that are very specifically focused on predictive maintenance and being able to look just at the predictive maintenance aspect of this. And then there are IoT platforms that provide a much more general approach that allow you to connect to a wide variety of different things within your factory and essentially create your own workflows around how you utilize that information. And obviously, given the title of the presentation, that last one is the one that we'll focus on today. So when we look at IoT platforms, here's an example from one partner of mine that shows a wide variety of different things and different use cases that you can utilize IoT for putting in place on your shop floor. And out of all those, OEE is really just one particular focus that can be put in place. So as we look at how we collect information from the shop floor and how we utilize that, the first step is to really create a complete profile of what your process looks like. And so the first step there is collecting that information from the machine or the sensors within the process itself. But the next thing that you really want to do is you want to contextualize that information with information like, what is the work orders associated with, what are the work instructions, the genealogy, who was actually working on that and what are they, what skills are they, qualified for and so forth. Any maintenance work orders associated with the machine and so forth. How does the bill of material break out for that item or the recipe in a process industry? And all of this information is going to help you analyze different aspects of that problem. So when you look at any particular problem and being able to do a root cause analysis on it, you'll want this information for that root cause analysis. But even more importantly, as you're looking at information over time and how things are trending, you're going to want to be able to correlate when failures occur with, when it's running particular products, when particular people are running that machine and so forth, and look for what are the contributing factors and how much those different factors contribute. If I look at where the manufacturing data comes from, certainly the devices and sensors on the shop floor are going to give a lot of information about the overall performance of the different pieces of equipment, as well as detailed information about the process variables or the tags from those PLCs as things are going. So just as a quick example there, if I'm looking at a grinding machine, I may look at the power draw on the grinding wheel in order to determine when I've got too much pressure, my power draw will go up. If I have quality issues and so forth, those might see different spikes or dips in my power consumption and so forth. And so there's a lot of things that I can get just from those devices and sensors. But then as I start kind of moving up in the organization, at the plant level, being able to capture environmental conditions, being able to look at, again, who's running it, what time is that job scheduled for, and being able to interact with all of those different things, supply chain and inventory, looking at different lot information, who is supplying different parts and so forth, and being able to trace all of that information, put that together, and continuing to go up through marketing and CRM and out to the market as a whole. And some of the things that we do at that level are working with things like warranty information and being able to correlate warranty information or escapes back to the shop floor and start to look at what was happening on the shop floor when those particular lots or those particular pieces were produced, so that we can start to do the analysis of what conditions do we see on the shop floor that are predictive of the things that end up in warranty eventually. And so, how do we change our testing routines to make sure that those warranties don't hit us downstream, or that the escapes to our customers don't occur. Just one quick example from a customer. We worked with a firearms manufacturer, and they asked us to create a corporate quality dashboard for them. They had 7 different primary manufacturing facilities. And when we first started the project, we talked to the IT department and asked, where the quality information is located. And they told us that, all the information is in SAP. And when I got done laughing, I asked them, no, really, where's the quality information? And so me and my team went out to the different plants. We talked to the different quality departments. We talked to people in warranty and customer service, and just built up our own list. And in the end, across 7 different facilities plus corporate, we found 57 different systems for quality alone that spanned several different areas. And that's actually not including systems that capture production information that is essential to interpreting the quality data. So there's information from all over the place. And one of the advantages of the I-IoT approach is that those systems are actually built in order to integrate different systems together and kind of recontextualize that information. And so if you're looking at something like a predictive maintenance system or a point OEE solution, they are generally not that good. They're built as data islands, and they're not able to take that information from the wide array of different and blend all of that information together in order to contextualize the data. Really, the next step that you want to look at is the difference between performance metrics and diagnostic metrics. And so a lot of systems will give you performance metrics. What is my first pass yield? What is my uptime? What's my downtime? What is my OEE? And that information is great, but it's like getting a report card and seeing a D in math for the semester for your child. Good information, but a little bit too late to do anything about it. And so, what you really want to do is you want to focus on the diagnostic metrics and be able to understand when individual events are occurring, what is the actual problem that's occurring, and what is the actual failure mode. And then if you can have some level of causal diagnosis each time, then you can start to categorize that information, add it up over time, summarize that, see the trends, and be able to put improvement projects in place to address those underlying issues. One more key aspect of that is once you have the diagnostic metrics that are kind of tying into those performance metrics, now what you want to do is you want to be able to dollarize those issues and to be able to see for each one of those different metrics or KPIs, what is the actual impact that has on the finances for the company. And being able to tie all of that together allows you, as you're collecting information on the shop floor, to be able to see, what is the actual impact? How far off am I from my standards? Am I having a good day or a bad day as a plant manager? And then being able to see what are the levers that I can turn in order to be able to impact that, as the day progresses, so that I can make every day a good day. From an augmented intelligence point of view, and being able to utilize predictive capabilities and prescriptive capabilities, we've talked about descriptive or performance metrics and diagnostic metrics. The next step is really to look at predictive capabilities as well as predictive or prescriptive capabilities. And predictive is all around what will happen, and prescriptive is around what should be done about it, and actually potentially automating those things as well. At the firearms manufacturer I talked about earlier, what we were able to do was to look at their loading operation, where they take the empty shells and they put the gunpowder in there. And what they have to do is they have to make a certain number of those, send them off to the test range. And the test range, of course, is in a different building because you don't want to be firing firearms in a building where you have raw gunpowder. And so they took them out of the building, took them to the firing range, fired them, wrote the information down about the pressure, the velocity, and the accuracy for the test, put that into an Excel file, sent that Excel file over to engineering. Engineering would take that, they would calculate what adjustments needed to be made in how many grains of gunpowder were getting loaded into each round. They would send that over to the supervisor, who would then work with maintenance to make the adjustments to the loader. And then they would have to do another test after that to make sure that everything worked out correctly. And that whole process would often span multiple hours. Well, the plant was in Arkansas, and the humidity and the ambient conditions can change quite a bit within those few hours. And as a result of that, what would happen is they would often have to create that new test sample, send it off to the firing range. Conditions have changed, so the pressure, velocity, and accuracy results changed. They send it back to engineering, and they go through this loop multiple times. Meanwhile, the machines are idle, not producing parts, and you're producing excess setup scrap, essentially. And so what we were able to do was to create one closed loop where the rounds still had to be, taken out of the building and to the firing range. But once those test results were captured, they went directly into a database. An algorithm was put in place to interpret those, utilize the rules from engineering, push that information directly to the controller for the loader, and do new rounds within 15 minutes. And so we compressed a cycle that would often take days and turn that into a 15-minute cycle where things would happen very quickly, and you very rarely had to go through a second round of optimization there. So that's prescriptive analytics. Being able to automatically identify, classify, and prioritize is another use case for the intelligence that you can put within here. And so I talked earlier about doing that classification of going from the descriptive or the performance analytics to what actually is occurring. And in addition to having people try to figure that out, you can actually utilize the intelligence within the system to automatically capture what is happening on the shop floor, and then interpret that information to try to classify different types of downtime. And so that's another use for these intelligence systems. And just some example use cases within manufacturing: predictive maintenance, vision systems, predictive tooling, predictive quality, furnace efficiency, monitoring lubricants and filters for when those need to be changed, warranty versus shop floor analysis that I talked about earlier, and so forth. So one of the great things about utilizing the I-IoT systems for working on OEE is that you can create any custom analytics or workflows that you wish to and employ those within your process. And so you can very much have the system match your process as opposed to having the process match the system. One key here is taking action. And for those of you who have heard me talk before, you've probably heard me use this example. But IoT system can very much be like a Fitbit on the shop floor, where I've been wearing a Fitbit for 8 years now and have probably gained 20 pounds during that time. And the reason isn't the Fitbit. The IoT device itself works great. It captures all my steps, captures my heartbeat, etc., pushes that information to a wonderful cloud-based application, big data store and so forth. It analyzes that information, provides analytics about my sleeping patterns and all kinds of higher level information. Has great charts and graphs and different interfaces for me on my phone, mobile device, on my computer, and so forth. And I still haven't lost the weight. And the reason is not the Fitbit. Again, it does a great job. The reason is that I haven't changed my behaviors, and I'm not taking action on the information that's being presented to me. And so it's the same thing with IoT systems on the shop floor. You still actually have to change the behaviors of your people in order to get the advantage of the information. And so one of the things that you can do with an IoT system is to actually set up a workflow so that when you see these problems, you automatically create actions for people to take. You get them assigned and you get that within their workflow. And so, depending on how you want to do this, and, assign that to operators versus supervisors, process engineers, or whomever, if you want to automatically create tickets within your maintenance management system, that can be done. And so a lot of this workflow can be established within these IoT tools in order to improve the process itself. In terms of the analytics that are presented to the user, one of the things that's very common with OEE systems or dedicated OEE systems or predictive maintenance systems is that it is incumbent upon the user to kind of explore the data and figure out where the problems are, and then analyze those problems, looking at the what, where, when, why, how, as well as the 5 whys and so forth, in order to identify what are the things that need to be done. And instead of doing it that way, you can present the users with guided analysis. And those guided analysis can be structured around a single topic, such as setup analysis or other items. And they help seek to help the user answer particular questions and lead them down a process to where they take action based upon that, as opposed to just presenting them information and letting them figure out what to do with it. Some examples of this guided analysis: you can automatically create real-time value stream maps with the information, as long as you're capturing what is being done in each step, the work order that's associated with that. Now I can track that work order from machine to machine and see what is my value add time at each machine, what's my non-value add time between machines, and a lot of other information that I can collect about the context of what's happening at each step. Setup analysis: how do you do your single minute exchange of dies or your SMED analysis? How do you reduce that setup time? How do you commonize that across your different workers and so forth? How much variance exists? What are the causes for variance? Tooling information: I'll go through a specific example around tooling at the end of the presentation. Production schedule for schedule versus production on time performance, schedule adherence, etc. Preventive maintenance, daily variable cost analysis, much more. These are just kind of off the top of the head examples of guided analysis that you can put in place. But you can also support other things like standard lean or TPM methodologies, for instance, creating a living FMEA. So if you have an FMEA that you've done for your process and you have identified your different failure modes, the effects of those failures, what is the actual cause of the failures and so forth, you can actually track what is the severity, what is the probability of occurrence, and identify what is your probability of detection by utilizing these as how you capture information on the shop floor. And if you tie the way that you're capturing the data on the shop floor into this process FMEA, you can automatically set your severity, your probability of occurrence, and so forth. Now, for a probability of detection, that's a little bit different. You have to figure out, how do I optimize my probability of detection? But utilizing the I-IoT systems and the flexibility that they have, you can actually use this to directly connect to any tag or any information about the process that is accessible. You can add vibration sensors or whatever else you need to in order to determine that particular failure mode is occurring. You can also then utilize this to increase that probability of detection if I need to infer it from a couple of different things that are going on. You can utilize the analytics capabilities to use that machine intelligence to then infer that this is the particular failure mode that is occurring. And by doing this, I can actually keep my severity and my probability of occurrence live and up to date at all times, and essentially have a live FMEA. And so this just kind of walks through that process of connecting to that machine data, Paretoing out the different failure modes, and then tying that back into the FMEA. You can utilize I-IoT systems to capture standard work and then present that to people, not only for the individual work tasks at the operator machine level, but also for capturing, what are the daily accountability checklists that you have for your supervisors, your process engineers, your management team, et cetera, so that they can go through that process, have that information prompted to them, and then walk them through that workflow. Modernizing visual controls out on the shop floor, instead of having something that looks like this, where you have people manually maintaining that information on a board. You can actually utilize that IoT system in order to provide that feedback out to the shop floor. Now, in terms of OEE and being able to improve your OEE, where I've seen this be tremendously effective is I had a customer that had a very low OEE on second and third shifts when the supervisors weren't there. And what we did was instead of hiring supervisors to be on second shift, third shift, at however many dollars per hour times hours in the year and so forth, what we were able to do is we were able to put big boards out on the shop floor at $1,000 per line. And by putting those boards out there that live displayed, how much downtime was accruing, what the performance was versus standards, and so forth, that essentially kicked in the Hawthorne effect. If you're not familiar with the Hawthorne effect, it's essentially when you have policemen on the side of the road, people slow down. People fundamentally change their behavior when they know they're being watched. And having these live visual controls on the shop floor actually themselves will produce a boost of 5 to 10%, especially if people are coming to them periodically and talking about what is on the board and the reasons why the performance is what it is. Then they know that those boards are being watched and they can see that their activities are being monitored and so forth. And so they behave differently. The Kaizen process itself, if you think about a typical 6-step Kaizen process of identifying problems, so I've got, at any given time, I have dozens of different issues going on in the shop floor. How do I decide which one I want to invest my resources in running an improvement event on? Analyzing the process itself, performing the root cause analysis, creating different solutions, and what is the solution space that I can look at, testing those solutions out, perhaps even simulating them in advance of making capital investments, measuring and analyzing the results, and then standardizing the solution, both at that process itself, so that when I take my resources away and put them elsewhere, I don't lose that improvement, but then also taking that improvement and putting it across all of my different lines, plants, et cetera, and having the software be able to help me kind of standardize that behavior across those different processes. Every single one of those can be enhanced utilizing the IoT solution. From a root cause analysis capability, this is generally the one that I don't get any pushback on whatsoever. Everybody goes, yeah, data helps. So if you look at something as simple as who, what, when, where, why, how, type of analysis of what is the context of different events and so forth, asking why 5 times and drilling down into the information, doing a fishbone or Ishikawa diagram, graphical evaluation, FMEAs, doing ANOVAs or design of experiments, et cetera. All of it is very highly data dependent, and being able to have that data context and detailed information available is critical to being able to do this accurately. Different maintenance workflows that you can put in place, and looking at how companies keep equipment running. So you have various maintenance practices, autonomous maintenance as part of TPM, preventive maintenance, also part of TPM, condition-based maintenance, predictive maintenance, then tying in those Kaizens and FMEAs and so forth into this as well. But looking specifically at those maintenance practices for a minute, from an autonomous maintenance point of view, having the operator do as much of those tasks on a daily basis as possible, being able to provide the operator with more information about what needs to be done, giving them a checklist essentially, notifying them when different things need to happen, as opposed to trying to track all of that on paper, or just counting on the fact that they'll know. Being able to track when it's actually done, and having some feedback to kind of check that off the list and so forth. Being able to change the duration between when different tasks are performed, from being done on a set schedule versus on an as needed basis, and being able to utilize the information from the process to prompt the operator when oil needs to be changed and so forth. And then having all of that be something that's presented in a very easy to consume, very easy to work with way is something that IoT is extremely helpful for. Preventive maintenance and being able to look at those PM tasks, essentially the same thing that we just talked about with autonomous maintenance, but higher level tasks around preventive maintenance, where you have the maintenance person that's responsible for those. All the things that I just talked about in terms of autonomous maintenance apply here as well. But being able to capture the work steps and everything else, and then present those in a way, whether it's on a computer screen or whether it's through smart glasses or anything else, to be able to present those instructions to the maintenance crew as they're working on that machine can lead to a lot of standardization and much better results in terms of how well that those tasks happen. Condition-based maintenance, and as I say on the slide, this is really where the power of these systems come in. Being able to look and perform these tasks around preventive maintenance, not just on a set schedule, but really when they are required based on things like temperature, vibration, power draw, etc. All of those things can be utilized to minimize the amount of time that you have to have the machine down in order to perform these tasks, but also maximize the efficacy of the things that you're doing. And then predictive maintenance is kind of the next step here of actually predicting the fact that given machine has a 90% probability of a particular type of failure mode within a given period of time. And you're going to be utilizing the same type of information in terms of temperature, vibration, power draw, et cetera, in order to predict those different things. But the system then can set up that workflow for you that actually prompts people to make those changes based on not just things going outside of a tolerance, but combination of different factors actually leading the system to predict when different failure modes will occur. When breakdowns do occur, how do we get the machine back up and running as quickly as possible in order to minimize the amount of total downtime that we have? Breaking down the reactive maintenance, we can look at that as when the failure occurs, what are the next steps that happen? Well, the first step is the operator has to be aware that a stop has occurred. And if you have a big line where an operator is running an entire, let's say, packaging line, if you have a failure, upstream at the filler and they're downstream, adding material, cardboard boxes into the cartoner and so forth, they may not be aware that the filler has had a stop for some time. And so how do you make them immediately aware when any of the different equipment on the line stops functioning? So then the operator is going to go over to that stop piece of equipment, and they're going to do some initial assessment to figure out, is this just a jam that they can clear on their own, or do they need help? So then once they decide that they need help, they have to somehow make maintenance or engineering or both aware that the problem exists, whether that's raising a ticket, making a phone call, sending a text, whatever mechanism is in place. Then the maintenance team has to take that information. They have to assign somebody to now go out to the piece of equipment. That worker has to become available. If they're not, if they're already on a task, they have to finish that task and then go to the different piece of equipment. They have to travel out to the machine, and now maintenance is actually there. So then maintenance has to diagnose the issue, and hopefully you have the right maintenance person there, because very often maintenance departments are split between electrical and mechanical people. And if it's if it's initially unknown or it's misdiagnosed initially, you may have the wrong person there and they may have to send somebody else, or that they can then fix the issue. So then the problem is fixed. Or if they weren't able to get the issue fixed, whether it was you needed somebody else, they didn't have the right parts, they didn't have the right tooling, any number of different reasons, then you have to try again later. And so if we look at why this doesn't get fixed on the first try, you could have the wrong repairman sent, you could not be able to diagnose the issue on the first try, you don't have the required parts in stock, you might have to leave the machine to go get parts from stock, you may need different tools than were brought to the machine, you may need different additional assistance to fix that problem, or you may not know how to make the repair. And so if we look at each of those individually, IoT can help with every single one of these things. So making the operator aware initially, if you have all of these different devices along the line hooked up to IoT, you can sense when they stop working immediately and make that visible to the operator, whether it's sending them a text message so that they feel the vibration on their phone, whether it's and-on lights or whatever it might be, that they can immediately see that something went down. In addition to that, if the system is able to diagnose the issue itself, and like we talked about with the FMEA earlier, be able to tie in the different the different tags to the different failure modes, now I can immediately let the operator know what type of failure has occurred, and they can determine right away whether or not they need help, or we might be able to make that assessment automatically. So then the IoT system can be tied into the maintenance management system, and you can automatically create not only a work ticket, but you can create that work ticket with the information from the process so that the right person is then assigned to that issue. And you have the right person respond to it right away with information about what type of failure it is, and what tooling may be needed, what spares might be required, so you have a much higher probability of being able to fix that issue on the first try. And so all of these things can be at least mitigated in many cases as well. So some customer examples. This is a bread manufacturer that we worked with where we collected information from each step along the process of that bread line. And for each time that it went down, we were able to collect information on what was the area, was it an equipment loss, production loss, quality loss, et cetera? What category was it? Was it in the oven? Was it late dough stages? Was it in the cooler, wrapping, et cetera? And then what was the actual cause for that? What product was running at the time? Who was operating the equipment, and so forth? And so when we look at that, we can actually trend that over time, and we see that every day we had a fair amount of downtime on a daily basis, and then we were able to actually dollarize that downtime as well. But if we start to drill into that and we just click on equipment loss, since that was the top bar there, and then we clicked on oven, which was the top bar underneath equipment loss, what we see is that we actually most days don't lose much time to the oven. However, we have these really big spikes when the oven does go down. And what we were able to determine very quickly by doing, by capturing some additional information when those did occur, is that the pins that were holding the conveyor and so forth would fatigue in the oven as they heated up and then cooled, and heated up and then cooled, and so forth. And the operators could tell you that that was an issue, but we had no idea how big of a problem it was, what frequency it was occurring, et cetera. And so once we had that information, we knew that it was worth putting a preventive maintenance task in place that periodically looked at those pins and replaced the ones that were fatiguing. And we completely eliminated the biggest source of downtime in that facility. Another example is with a customer that does grinding, and has these grinding wheels that they were stopping the machine every 120,000 pieces, and they make tens of millions of pieces a year, and they were spending $200,000+ every year replacing or refurbishing these grinding wheels. And 50% of them are removed before reaching failure. For the 50% that reach failure, now you're producing bad parts. And so how do you get as much life as you can out of each wheel, but not put yourself at risk of producing bad parts that then go downstream? And so what we did was we put a system in place that captured information directly from the machine PLC, as well as putting some other sensors in there to capture vibration and noise, et cetera. And we pulled that into ThingWorx, which was the particular partner I was working with on that account. And we built the logic within there in order to be able to basically cleanse that data as it came through, store the information and so forth. Then we ran it through the analytics within the tool in order to be able to look at what was the typical performance when we had a worn wheel versus a new wheel, and what the failure mode looked like as well. And so based on this information, in terms of the amplitude and the variance, we were able to very confidently predict when these wheels were approaching the end of life, and make the change before a failure occurred, but getting as much life as we could out of those wheels. And then we were able to present that on a computer or tablet, mobile device, as well as augmented reality type of visibility. So with that, I want to thank you for your time today, and I want to reach out to you and follow up and make sure that if you have any questions, I can get them answered. If you want to, please reach out to me at tim@visualdecisions.com, or my phone number there on the screen. The presentation will be available on my website within the next day or two, as well as the presentation will be available for download. So thank you very much, and I look forward to talking to you in the future. Bye.